Dictionaries, a set of n records, each identified by one or more keys, build and maintain a data structure to efficiently locate, insert, and delete the record associated with any query queue. The abstract data type dictionary is one of the essential structures in a computer science. Many data structures have been proposed for implementing dictionaries, including hash tables, skip lists, balanced and unbalanced binary search trees. This means that choosing the best one can be tricky. However, it is more important to avoid using a wrong data structure than to identify the best option available. To choose the right data structure for your dictionary, answer the following questions. How many size? How many items will you have in your data structure? Will you know this number in advance? Are you looking at a problem small enough that a simple data structure will suffice? Or one so large that we must worry about running out of memory all or virtual memory performance? Do you know the relative frequencies of insert, delete, and search operations? Static data structures, like sorted arrays, suffice in applications when there is no modifications to the data structure after it is first constructed. Semi-dynamic data structure, which supports insertion but not deletion, can have significantly simpler implementations than fully dynamic ones. Search query access pattern. Search queries exhibit a skewed access distribution in many applications, meaning certain elements are much more popular than others. Further queries often have a sense of temporal locality, meaning elements are likely to be repeatedly accessed in clusters instead of regular intervals. Data structures such as splay trees can take advantage of a skewed or clustered universe. Options: unsorted linked lists and array. An unsorted array is the easiest data structure to maintain for small data structure. Linked structures can have terrible cache performance compared with sleek, compact arrays. However, once your dictionary becomes larger than say 50 to 100 items, the linear search time will queue you for either lists or arrays. A particularly interesting and helpful variant is a self-organizing list. Whenever a key is accessed or inserted, we move it to the head of the list, thus the key will be near the front if it accessed again shortly, and so it requires only a short search to find it. Most applications exhibit both uneven access frequencies and locality of reference, so the average time for a successful search in a self-organizing list is typically much better than in shorter or sorted or unsorted lists. Self-organizing data structures can be built from arrays and linked lists and trees. Sorted linked lists and arrays. Maintaining a sorted linked list is usually not worth the effort unless you try eliminating duplicates, since we cannot perform binary searches in such data structure. A sorted array will be appropriate if there are not many insertions or deletions. Hash tables. A hash table is the right way for applications involving a moderate to large number of keys. We use a function that maps keys, be they strings, numbers, or whatever, to integers between 0 and m-1. We maintain an array of m buckets, each typically implemented using an unsorted linked list. The hash function immediately identifies which buckets contains a given key. Presuming the hash function spreads the key out nicely through a sufficiently large hash table, each bucket should contain very few items, thus making linear search acceptable. Insertion and deletion from a hash table reduce to insertion and deletion from the bucket list. Binary search trees. Binary search trees are elegant data structures that support fast insertions, deletions, and queries. The primary distinction between different types of trees is whether they are explicitly balanced after insertion or deletion, and how this balancing is done. In simple random search trees, we insert each node at the leaf position where we can find it with no rebalancing. Also, such trees perform well under random insertions. Most applications are not random, indeed, unbalanced search trees constructed by insertion keys in a sorted order are disaster, generate, uh, degenerating into a linked list. Balanced search trees. Balanced search trees use local rotation operations for restructuring, moving more distant nodes closer to the root while maintaining the in-order search structure of the tree. Among balanced search trees, AVL and two search trees are now passed, and red-black trees seems to be most popular. A particularly interesting self-organizing data structure is a splay tree, which uses rotation to move any accessed key to the root. Frequently used or recently accessed nodes thus sit near the top of the tree, allowing faster searches. Bottom line. Which tree is the best for your application? Probably the one of which you have the best implementation. Which flavor of the balanced tree is likely not as important as the skill of the programmer who coded it? B trees. Your best bet for a large dataset that will not fit into the main memory will be some B tree flavor. The search time of a data structure grows by several orders of magnitude once it's stored outside of the main memory. With modern cache architecture, similar effects can happen on a smaller scale because the cache is much faster than RAM. The idea behind B-tree is to collapse several levels of binary search tree into the single large node so that we can make the uh, equivalent of several search steps before another disk access is needed. B-trees can access enormous number of keys using only a few disk accesses. To get the full benefit from using B-tree, it is critical to understand how the secondary stage device and virtual memory systems interact, particularly constants such as page size and virtual real address space. Cache oblivious algorithms described below can mitigate such concerns. Even for modest-sized data sets, unexpectedly poor data structure performance may result from excessive swapping, so listen to your disk to help decide whether you should be using a B-tree. Skip lists. These are somewhat of a cold data structure. A hierarchy of sort linked list is maintained where a coin of is flipped for each element to decide whether it gets copied into the following highest list. This implies roughly log n list, which roughly half as large as the one above it. Search starts in a minor list. The search key lies in the interval between two elements, which is then explored in the following larger list. Each searched interval contains an expected constant number of elements per list for a total expected O from logarithm n query time. The primary benefit of skip list are ease of analysis and implementation relative to balanced trees.